Greetings! Welcome to Electronic Circuits 1. I am Behzad Rozavi and this is lecture number 35. Today we will begin to look at CMOS technology and CMOS amplifiers. Now that we have learned how MOS devices operate both N-type and P-type transistors. Before we delve into things, let's take a look at the last lecture and see what we covered. In the last lecture, we developed the small signal model of the MOS transistor, including channel length modulation. And we saw that in addition to the voltage-dependent current source that monitors this voltage and converts it to a current by a factor of GM, we also have a resistance between the drain and the source that models the variation of the drain current when the drain source voltage varies. And that has to be there if you want to be precise. And again, in some cases we neglect it, in some cases we don't. And then we also talked about the analysis of CMOS circuits and how we go about doing that. And we said that the first step is to calculate the bias conditions for the MOSFETs. We find their gate source voltages, the drain source voltages, etc. We make sure that they are all in saturation, because that's what we need for proper operation, at least in this course. And then from there, we can find their small signal properties, because once we have the voltages around the transistors and the drain currents, we can calculate GM, we can calculate RO, etc. All right, and then we talked about the PMOS device a little. We saw that in the PMOS device, everything is flipped. The type of doping that we have for the substrate and for the source and drain has changed, and as a result the current is now carried by holes rather than electrons. The current flows from source to drain in the form of holes, so the drain current, if it is pointed into the drain, will be a negative number. And because the gate has to be less than the source voltage by some amount, more negative than the source voltage, to ensure that we attract holes to the oxide interface, we use a negative VGS for the device. Similarly, we use a negative VDS for the device, again because we would like the holes to start from the source and go to the drain. Now with these conditions, everything is flipped with respect to the NMOS device. The source voltage is more positive than the drain voltage in a PMOS device. Now, because in electronic schematics, we would like to draw more positive voltages and lines on top of the page, we generally draw a PMOS device with its source up here, not down here. It's not required, but that's what happens most of the time. So now if we draw the small signal model of the PMOS device, which is identical to that of the NMOS device, but because we have flipped things, it looks like this. The gate is down here, the source is up here, the drain is down here. We still have a current source equal to GMV1, just like before, going from drain to source. So it goes from drain to source. This arrow points from drain to source. And then we have an RO. So you see that this model and this model are identical, except that we flipped it here because in the schematic we had flipped the transistors. All right. So today we'll talk a little about what we call CMOS technology, which stands for complementary MOS technology. And complementary MOS technology means that we would like to have both NMOS and PMOS devices in our circuits. So that's complementary MOS technology. It turns out that if we have both NMOS and PMOS devices, it is a tremendous flexibility in circuit design. This is unique. Okay, well, how do we do that? Well, we have a bit of a problem. Let's draw the cross-section of the NMOS and the PMOS devices and see what we have. So here's our NMOS devices with N plus here, N plus here, and a P substrate. And then we have a PMOS device, like so. where we have P plus here, and an N substrate. Okay? Now, when I go and buy a wafer to build these transistors on top of it, the wafer comes with a certain type of doping. I can say I would like an N-type wafer or a P-type wafer. Okay, the only one of the two. So now, let's say I start with an N-type wafer. So here's an N-type. Let's say we start with a P-type wafer. So here's a P-type wafer, right? And then we go ahead and build our NMOS devices. Not a problem. But then how do I build this PMOS device on an N-type wafer? Because this PMOS device likes to see on a P-type wafer. This PMOS device wants to see an N substrate, whereas the wafer that we bought is a P-type wafer. Right? But there's a clever solution for this. So here's how the solution works. We start out with a P-type wafer, P substrate. And these wafers are about 300 microns thick, if you're interested. And then we build an NMOS device like so, N plus, and gate and all that. Now we're going to build a local N substrate for this particular transistor. And that is a big piece of N that is created on top of this wafer, which we call N well. It looks like a well, right? Now, inside this N well, we can build the PMOS device. So here's our PMOS device, P plus here, and then we have the gate. So now we have both NMOS device and PMOS device using a P-type wafer. This is called CMOS technology because we have complementary transistors. What's interesting is that the first few generations of CMOS technology, of MOS technology back in 1960s, early 70s, were using only NMOS devices because of technological limitations and cost limitations. And in fact, many people said going from here to here is just too expensive. This is not worth it. We should not do this. We should stay with only N-type devices. But as they say, that's history. And what happened in early 70s and so, we gradually went from only N-type devices to P-type complementary devices. And now, of course, this is the dominant technology that we have. All right. If you have taken digital circuits using MOS devices, you have seen, for example, the CMOS inverter, which relies on NMOS and PMOS devices. In fact, most static logic circuits that use MOS devices rely on both NMOS and PMOS. If you take the PMOS away, it's a very difficult design, a very power-hungry design. All right. So that is CMOS technology, and now we have access to both of these, and that's how our designs will proceed. Sometimes we use NMOS, sometimes we use PMOS, sometimes we use both, so we will see those. All right, before going further, I wanted to have a quick exercise on the regions of operation of NMOS and PMOS so that some of these ideas are hammered in better. So let's go over a quick example here. Now, what we do remember is for an NMOS device to stay in saturation, we said that the drain cannot be lower than the gate by more than one threshold. All right? The drain cannot be less than the gate by one threshold. If the drain is too low, the device goes into triode region. For a PMOS device, if you draw it like this, doesn't matter, you can draw it that way, we said that the drain cannot be higher than the gate by more than one threshold, one absolute value of threshold of this PMOS device. So the edge is always determined by the threshold voltage. If this difference is one threshold, we are at the edge. If this difference is one threshold of the PMOS device, the absolute value, then we are at the edge. And we know what happens if we go one way or another. If we are here and the drain goes lower or the gate goes higher, we enter the triode region. If we are here and the drain goes up or the gate goes down, we enter the triad region. So that's what we have to remember. These two pictures will help us analyze the regions of operation of any circuit. Okay, so here's an example. Let's take a MOS device like this. I deliberately draw it like this to confuse you. And for example, let's connect the gate. I connected this to 0.8 volts, and this one to 0.1 volt, and this one to 0.9 volts. So in your head, you can assume there are 3 batteries connected from here to ground, from here to ground, from here to ground, or all connected to one point. And these are the relative voltages from here to some reference voltage. Okay, so now let's assume VTH N is equal to, for example, 0.5 volts, and VTH P is equal to minus 0.6 volts. And we would like to see which region of operation we have here. First, we have to decide if the device is on or off. And then if it's on, is it in triad region or is it in saturation? Okay, well, what can we say? Well, the gate is at 0.8 and the source is at 0.1. So VGS is 0.7 volts. So we write that before we forget. So VGS equals 0.7 volts. All right, so VGS minus VTH, 0.7 minus 0.5 is 0.2 volts. So the overdrive is 0.2 volts. VGS minus VTH is 0.2 volts. Okay. All right. How about VDS? VDS, 0.9 minus 0.1 is 0.8 volts. So VDS is equal to 0.8 volts. Well, we see that VDS is greater than VGS minus VTH, so the device in saturation, no problem. The device is on because VGS is greater than one threshold, and the device in saturation because VDS is greater than VGS minus VTH. So we say this device is in saturation. No problem, we move on. Let's look at another circuit where I did this. I have 0.8 volts here, 0.8 volts here, and 0.2 volts here. How about this? Okay, so first question, is this on or is this off? You might say, well, the gate is at 0.8 and the source is at 0.8. The difference is 0, the device is off. Well, not quite. How did I decide this is a source? Just because there's an arrow on it, it doesn't mean it's a source, right? So sometimes we draw the source just to indicate that it's an NMOS device, just that, right? But we don't really know if this is the source. What's the definition of a source? The source is the terminal of the NMOS that is lower in potential than the drain of the NMOS, right? The drain has to be higher than the source. Now, if you look here, which one of these would be a candidate for the source and which one would be candidate for the drain? Well, this one has a lower voltage than this one. So if we want to choose, we have to say this would be the source and this would be the drain, not the other way around. Not because there's an arrow on it. Okay, so that's a tricky point. All right, so we'll make sure that this is highlighted properly. The terminal between source and drain, the terminal that has the lower potential has to be the source. So this is the source, and this is the drain. Okay, so now let's ask the same question again. Is the device on or is it off? It is on because gate source voltage is 0.6 volts. So VGS is equal to 0.6 volts, greater than one threshold, so the device is on. And which region of operation do we have? Well, we write VDS. VDS is the drain voltage minus source voltage, that's 0.6 volts. And that's greater than VGS minus VTH. So the device is in saturation. Okay, very good. No problem there. Now let's switch gears to PMOS devices. I will draw a PMOS device here, and again I have an arrow just to show it's a PMOS device. I don't really know if that's a source or not. And in this example I have chosen 0.1 volt here, 0 here, and 0.8 volts here. First question, is the device on or off? Okay, well, first we have to decide which one could be the source, which one could be the drain. We know that in a PMOS device, the source has to be more positive than the drain, right? So which one of these could be the source? This has to be the source, and this has to be the drain. So this is the source, and this is the drain. Okay, now for a PMOS device, the gate source voltage has to be negative, in fact more negative than the threshold for the device to be on. Do we have that situation? So gate source voltage is minus 0.8, right? So VGS is equal to minus 0.8 volts, which is more negative than the threshold. So the device is on. That's good. And now we have to decide if we are in saturation or the triad region. Okay, so we find the overdrive voltage, VGS minus VTH. So VGS minus VTH. So we have minus 0.8 plus 0.6, so that's minus 0.2 volts. All right, that's the overdrive voltage. Okay, how about the VDS? VDS, drain minus source, is equal to minus 0.7 volts. Okay, now in cases like this, if this is confusing, you can try to redraw this device in this form, because that form is something more familiar to us. So let's do that for a second and see. All right, this is the source. So the source has to be drawn on top of the page, and the arrow actually goes on this one now, because it's the source, right? Okay, how much is the gate? The gate is at 0.1 volt. The drain, the source, is at 0.8 volts, and the drain is at, sorry, the gate is at 0. Let me erase this. The gate is at 0. The source is at 0.8, and the drain is at 0.1 volt. All right, so are we in the triad region or in saturation? We look here. We said that when this difference is plus 0.6 volts, we are on the edge. Well, we are only at 0.1 volt difference, so we are far from the edge, except that which way did we go? Did we go farther into saturation, or did we go farther into the triad region? Well, we know that we begin to go towards the triad region as this drain goes higher and higher above the gate, right? But here we see that the drain is lower. The difference between these two is only 0.1 volt. So the device is in saturation. And that can be also confirmed by writing VGS minus VTH is greater than VDS. So the strange thing here is that this equation is different from the type of equation that we had before, for example here, right? Because these are all negative numbers. That's why writing these negative numbers might be confusing, and this picture might be much better to visualize than just rely on the equations. But however you want to do it is fine. You just have to remember how these are interpreted. Okay, so this is necessary for a PMOS device to be in saturation, given that this is negative and this is negative, right? So, and then you can, or you can look at it this way instead of writing the equations blindly. All right, the last example I wanted to show you is another one like so. So again, we have a PMOS device, and the gate is connected to 0.1 volt, and the source and drain to 0.8 and 0.6. 0.8 volts and 0.6 volts. Okay, so again, we would like to see what the device is doing. First, is it on or is it off? Well, to get there, first we have to decide which one could be the source, which one could be the drain. The source has to be more positive than the drain for a PMOS device. So this is more positive than this. So actually, this is the source. So great, the arrow stays where it is. All right, that's the source, that's the drain. Now, the gate source has to be negative enough, more negative than the threshold. Is it? Yes. VGS is minus 0.7 volts, but the threshold is minus 0.6 volts. So we're good. The device is on. So we say VGS is equal to minus 0.7 volts. The device is on. All right. So let's calculate the overdrive voltage if you want to just stay with equations. So we say VGS minus VTH is equal to minus 0.7 plus 0.6, so that's minus 0.1 volt. And VDS is equal to minus 0.2 volts. So minus 0.2 volts. So because VGS minus VTH is greater than VDS, like before, we would expect that this is a saturation. And again, if you are in doubt, we go back to this picture. So let's redraw that with the source on top. So the source is at 0.8 volts. The gate is at 0.1 volt. And the drain is at 0.6 volts. So it's that the drain is higher than the gate by 0.5 volts, right? 0.5 volts. Whereas here, to be on the edge, you would need the drain to be higher than the gate by 0.6 volts. So because the drain is not too high, this device is in saturation. So that's good. It agrees with our equation. All right, it's always good to draw some devices like this, give them some arbitrary voltages, and go through this exercise. It strengthens your understanding of saturation and triode and on and off. Today in Frontiers in Electronics, we will look at one application of electronics in our daily lives, and that is the automotive radar. So, as we know, most cars today have some sort of radar, and it is predicted that in the next few years, the use of radars in cars will be even more prevalent. This is because we want to use radars to accommodate drivers in the cars without too many accidents, etc. So, in fact, it is predicted that by the year 2020, we will have self-driving cars, autonomous cars. And obviously, for a car to drive by itself on the road and be aware of its surroundings, of other vehicles or other obstacles, the car needs to have radars to detect all these things. So even though radar was considered more of a military device back in 1940s when it was invented, now it is becoming more of a consumer device. And it has found its way into automotive applications. So we have automotive radars. As I mentioned, we also have, of course, military applications. We have navigation. Whether it's on a ship or on a commercial airplane, we always have radars to be able to scan the environment and detect various objects. And many other ones that we won't go through. Today I just want to concentrate on automotive radars and see what they do. So automotive radars play a number of roles in a vehicle. So here are some of the things that they try to do. So first is blind spot detection. When you're driving and you want to change lanes, if you don't look right at this angle to see if there's any car on that side, well, you might change and then you hit that vehicle. This is called the blind spot, and radars on the two sides of the car can detect. And if there is a vehicle on that side, the car will not allow you to go to the other lane. So that's a great feature. Then we have parking aid. So if you're trying to park in a narrow space, or you're trying to back into a space and you don't see the back of your car very well, or the wall very well, as soon as you get too close, the radar goes off and gives you a warning so they don't go any farther. So that's also good. And then eventually for cruise control, and what we call self-driving cars. In fact, as I understand it, even by the year 2017 or 2016, there will be some cars on the road that can go into autopilot. So you press a button, you sit back, and the car will drive by itself. So that would be very interesting to try. Okay, so we want to look into radars and see exactly what it is that they do and how they become useful for these functions. Well, radars actually were invented after people understood how bats operate. When bats fly at night and they don't have any vision, how do they find their way? How do they find the prey, etc.? So it was very interesting how they discovered this. So radar is based on that operation, and it's very simple. Here's the basic idea. So radar operation. In bats, it's called echolocation. We send a wave. The wave has an echo, a reflection, and from that reflection, we can, for example, determine how far the object is, right? So imagine that you have your vehicle. Here's a vehicle, and you send a wave out. So you send a wave out, an electromagnetic wave, and this hits another vehicle. So here's another vehicle that's right in front of you. Now, you might be going towards each other, or you might be going away from each other. In any case, this wave hits this car, and then it's reflected. So it comes back, and is received by you. So from the time that this wave takes to go there and come back, this is called the round trip time, we can determine the distance between these two. Not a big deal, right? Light velocity divided, the time divided by light velocity, time divided by 2 gives us this distance. So we can determine the distance from the round trip time of this wave. We send the wave, and we wait for it to come back. As soon as we receive it, we measure the time difference, and from there we can find the distance. But there's one more thing we can do, and that's the speed of this vehicle with respect to us. So we can find the speed or velocity. How do we do that? Well, suppose that these two vehicles are coming towards each other. When we send a wave from here and goes back and hits the car and comes back, the frequency of the wave changes. This is called Doppler effect or Doppler shift. If the cars are coming towards each other, the frequency of the wave that we receive goes up with respect to what we transmitted. If the cars are going away from each other, the frequency of the wave that we receive goes down. The wavelength increases. So the speed is determined by the Doppler shift in the frequency or wavelength, same thing, right? Okay, so based on these two principles, we can determine the distance and also the relative velocity of these two vehicles. So that's great. We can predict what's going to happen in the next second or 10 seconds. All right, so let's try to build a radar system based on these principles. We need to transmit a wave out this way. All right, how do we generate a wave? Remember from the Bluetooth example? So here, I'll put the Bluetooth example up here so that you can remember. In the Bluetooth example that we studied a long time ago, we said we take an oscillator, we generate a periodic waveform, and give it to a power amplifier to create a large waveform, and then we transmit it out. So in the radar, we do exactly the same thing. We have an oscillator that generates a wave, and then that wave needs to be amplified so that it has a reasonable range. Let's say you want it to go 100 meters, then it come back 100 meters. So we have an oscillator. This is a symbol for the oscillator. And that oscillator goes through a power amplifier, PA, and then we generate this wave. And this wave comes out and goes and hits the object, and then comes back. So when it comes back, now we have to sense it. We have to receive it. So this is what you call a transmitter, TX. Now we need to build a receiver, RX. So we have another antenna, and here's the wave that's coming back to us. We receive that wave. Now what do? Well, just like the Bluetooth example, first we amplify it. So I'm drawing the signal going this way. If you remember, we have a low noise amplifier to amplify the wave that has been received. And then we have to process it. So we'll just put a box here for now. We call it processing. And this processing has two objectives. Number one, try to measure the travel time of this waveform, of this wave, that as it went and hit the object and came back. From the travel time, we can find the distance. And it also tries to measure the frequency difference between this waveform and this waveform. And that frequency difference can tell us what speed we have. That's the operation of a simple radar, one type of radar. And these radars will be used in abundance in future vehicles. That is our application for today. Okay, we are now ready to go to CMOS amplifiers. Let's begin and take a look at the CMOS amplifiers. All right, so we want to build circuits that can amplify. Where can we use amplifiers? Well, we've seen them in a number of places. In our Bluetooth transmitter, we had an amplifier. In our Bluetooth receiver, we had an amplifier. A similar situation with the radar application. We have a microphone here. This microphone has to amplify my voice and then give it to this device that wirelessly transmits it to the device connected to the camera. The camera receives that signal, amplifies it, and then records it. So all of these require amplifiers. And these amplifiers have different frequencies, different speeds, various different parameters. Okay, so to study amplifiers, the first thing that we will try to do, let me get all of this under control here. All right, so we will, to build amplifiers, to design amplifiers, this is what we need to do. So, amplifier design procedure. Number one, we select an amplifier topology. As we will see, we have different amplifier topologies, and then they have different properties. One topology might be useful for this application, another one for another application. Based on that, we go ahead and choose one. Then we bias the transistor or transistors to obtain proper values for GM, RO, etc. for the small signal properties of the device. As we will see, the overall characteristics of amplifiers heavily depend on the small signal properties of the transistors, whether we have a high GM or low GM, high RO, low RO, and so on. So for each device, we have to bias it properly. If you remember from our previous examples, if the device has no bias current in it, the device is dead. If there's no amplification, we can't use it. So we do have to bias it up before we hope any amplification will occur. Okay, so, and then determine the characteristics of the circuit, of the amplifier. So now that we have biased up the circuit, we can create, for example, a small signal model and analyze it and find its characteristics. But what characteristics are we looking for anyway? So here are the amplifier characteristics that we are looking for. So amplifier characteristics. Yes, only for the purposes of this course, because there are numerous characteristics that an amplifier might have to satisfy. But we have to simplify and simplify and simplify so that at least it's something we can begin with. So, number one, what we call gain. Gain shows how much amplification we have. So, for example, you have an amplifier here. You give it a little sinusoid like this, and then you get a big sinusoid like that, right? So this swing divided by this swing is called the gain of this amplifier. Typically, we are interested in amplifiers that take a voltage and generate a voltage. So this would be called the voltage gain of the amplifier if we divide this voltage swing by this voltage swing. So oftentimes we call this voltage gain. There are some rare cases where we are interested in other types of gain, but in most cases we are interested in voltage gain, and it is denoted by A sub V, voltage gain. For example, the voltage gain of an amplifier might be 10. If you give it 2 millivolts peak to peak, let's say to this microphone, then the amplifier generates 20 millivolts peak to peak. All right, what other characteristics are we interested in? Well, power consumption. How much power does the amplifier take to provide this gain and other characteristics? So power dissipation is important. Power dissipation or consumption, both are used. For example, in portable devices, you don't want to charge your cell phone all the time. You still have to charge it at the end of the day, but sometimes you can if you have a very low power consumption cell phone, you can keep it for several days and then charge it. So that's one example of why power dissipation is important. Remember that we are biasing our transistors so they have a current in them at all time, right? Even though there's no signal, they still have a current. And that current is coming from the battery, so it drains the battery out. And that's why the amount of current, the amount of power that we need to provide to the amplifier for it to be a good amplifier is important. All right, and there are many other ones. So I'll just put some dots here to indicate that amplifier characteristics include many other ones that we don't talk about right now. We come back to some of them a little later. Okay, very good. So in the next step, we want to build an amplifier. We have tried this a number of times since we started looking at CMOS devices, right? We said, let's build an amplifier, and we made a number of attempts. So I will quickly summarize those attempts and see where we are right now. So I'll write again, let's build an amplifier. All right, so we started out a long time ago by saying that if we have, let's say, a microphone signal, and we want to amplify it. A microphone generates a voltage, a time-varying voltage. So what we can do is we take this voltage and give it to a voltage-dependent current source. So we have voltage to current conversion, right? So we have some sort of voltage here, V1, and this is some dependent source that we buy, and it generates a current in proportion to this voltage, kV1. We let that current flow through a resistor, RL. That gives us a voltage, and by proper choice of K and RL, I will have some gain. Right? That's how we conceived it at the beginning. Then we said, oh, well, actually a MOS device looks like a voltage-dependent current source, so why don't we do that? So in the next step, we took that current source, that dependent current source, replaced it with a MOSFET like this, and passed the current through a resistor, RL, and we thought that this might be an amplifier. Unfortunately, it wasn't, because in the absence of a signal, the gate source voltage is 0, the device is off, there's no amplification. We said, okay, well, why don't we place a voltage source, a battery, in series with this microphone to ensure that when there's no signal, we still have a respectable VGS. So in the next step, I'll draw it up here, we said, okay, here's what we do. We place the microphone in series with the battery. This battery has a voltage of V0, and then we pass this through a resistor. So now, when the microphone has no signal, VGS is still equal to V0. V0 can be higher than the threshold voltage, so the device is on. But then we saw that we cannot have any current in this loop because there's no source of energy here, right? We need a battery to have current to continue to flow. So that didn't work. We said, okay, let's go and change it to this. We try to insert another battery in series with this resistor. So that's what we call V1. And this is V0, and that's RL. And the idea was that now a current can flow from this battery through RL, through the device, back to the battery. So we can establish a current here. And we can choose the numbers such that this device is in saturation. It has to be in saturation. So we want this voltage, the drain voltage, not to be too low. It can be as low as one threshold below the gate voltage. Okay? That's the minimum it can go. So we have to choose this resistor, the voltage drop across the resistor, and this voltage source so that happens. Okay. All right. This is a pretty good amplifier. I'll just have to draw this resistor vertically just for illustration purposes, not a big deal. So let me draw that like this. There's no change in the circuit. I'm just drawing it differently. All right, so here's a microphone. Here's a battery. And here's another battery. We have V1, V0, and this is RL. So if there is no signal, this microphone generates 0 volts. VGS is equal to V0. We have a certain current. That current flows through this RL. We have a certain voltage, and that's it. That's where we are. Now, if I speak into the microphone like this, then what happens? Well, this VGS begins to change with the microphone signal, which means this current begins to change, which means this voltage begins to change. And that's how we are hoping to build an amplifier. Just like this, right? That's what we did. The microphone changes this voltage generates a current, this current flows through the resistor, this voltage changes, that's our amplified voice, so it comes out. All right, well, so where is the output voltage anyway? Remember that here we had an input voltage and an output voltage, right? So where's the output voltage? Well, you might say the output voltage is right here across this resistor, right? We took the current and converted it back to voltage by running it through a resistor. Why the resistor can do that? The resistor can convert a current to a voltage. Sure, let's do that. Let's look at that for the moment. So we will call this VRL, the voltage across RL, and see what happens. All right, now what I would like to do is the following. I would like to plot some of these voltages as a function of time because it gives us additional insight. All right, so let's do this. Let's plot first the gate source voltage of the device as a function of time. This gate source voltage here. First, assume there is no microphone signal. So this voltage is 0, and VGS is equal to V0. So in the absence of a signal, we just have a constant bias voltage of V0. All right, that's great. Now the signal comes in from the microphone. Let's assume a sinusoid for simplicity. So we have a sinusoid coming in. That's what we get for VGS. A little sinusoid is riding over a level of V0. Okay, now let's go ahead and plot this voltage across RL as a function of time. So here we have T, here we have VRL. Okay, so again, assume there's no signal. If there's no signal, we have VGS equals V0. There's a certain voltage here. This voltage generates a certain current. So there's a certain current flowing here, which we usually call ID0, just a bias current, right? There's a bias current flowing, and it's not changing with time because the microphone signal is 0. Okay, so if this current is ID0, how much is this voltage? ID0 times RL. So in the absence of a signal, the voltage drop across RL is equal to ID0 times RL. All right. Now the microphone signal comes in. That begins to modulate this VGS. This VGS changes, which means this current changes. And if this current changes, this voltage changes. Now, just one little interesting note. If VGS increases, right, if VGS becomes more positive due to the microphone signal, so here you see VGS is increasing, what happens to VRL? Well, VRL also increases because we have a larger current now, right? We draw a larger current. So that also goes up, and maybe it does this because we're hoping to build an amplifier, right? So we have a small swing and we get a large swing. All right, that's great. Okay, but in practice, we prefer to take another voltage from the circuit, not the voltage across RL. And the reason for that will become clearer later. So what we really want to take, let me change the color of my pen, is the voltage difference between the drain and this point here. We prefer to look at this voltage and we call it V out. Okay, we prefer that. You see that this is sort of a common terminal to all of these, a common rail, we call it, or a reference point, if you remember from circuit theory courses, or a ground, as you might remember from those courses, right? So we call this ground. It's common to all of these. And we prefer to measure the voltage at the drain with respect to this ground. Let me put a symbol of ground here. This might be familiar to you. So that's called the ground. This doesn't mean that it's necessarily connected to the ground. It's just a notation to simplify things. Okay, so let's try to plot this voltage also as a function of time. All right, so here's T. Here's V out. In the absence of a signal, what happens? Well, V out must be constant, right? It doesn't change with time. And the question is, how much is V out? So I will give you 90 seconds to think about that. Okay, so what did we get for V out? Well, we can write a KVL around this loop. We have V1 here, we have VRL here, and V out here. So, for example, I can say VRL plus V out, these two are on top of each other, must be equal to V1. So we have VRL plus V out equals V1, which means V out is equal to V1 minus VRL. In the absence of a signal, VRL is given by ID0 times RL. So it's equal to ID0 times RL. Okay, so that's the voltage that we have right at this point before a signal comes in. It's a certain amount. We do expect V out to be lower than V1, right? Because V1 is from here to here, let's say 2 volts, but then there's some drop from here to here. So this voltage has to be less than this voltage, and that's what we see here. Okay, now the microphone signal comes in. Let's suppose, again, that VGS is increasing because of the microphone signal, which means the drain current of the device is increasing. Now what happens to V out? Well, because the drain current is increasing, V out decreases. As we draw more current from this resistor, this voltage goes down because this point is fixed, right? And RL needs a greater drop on it because the current through it is increasing. So the only way is for this voltage to go down. That's a critical point. So now V out begins to go down, and it goes up, and goes down, and goes up, and so on. Okay, so what we see is that the swing that we generate here is the same as the swing across RL. The total change is just that this DC level is different from this DC level, right? This DC level is ID0RL. This DC level is V1 minus ID0RL. But from now on, we will take this voltage as the output voltage of this circuit, this amplifier. All right, congratulations. We have built our first CMOS amplifier. This amplifier is called a common source stage. So we will draw it again here. And this is V out from here to here. And we have some bias voltages, V0, then V1, some resistor up here. And we might also call the transistor something M1 if you want. And this is called the common source amplifier or common source topology. The definition of a common source topology is very strict and is as follows. So I'll change the color of my pen to show you what we mean by that. Definition is as follows. The input to the amplifier, remember we have an input, right? The input to the amplifier goes to the gate of the transistor. Not to the source, not to the drain, but to the gate. So we say the input is applied to the gate. And the output of the circuit, this output, is measured, is sensed, is taken at the drain of the device. So the output sensed at the drain. The output is not taken at the source, is not taken at the gate, it's taken at the drain. So when we have this condition and this condition, we have a common source amplifier. That's how we identify a common source amplifier. Okay, so we have this amplifier. And what we would like to do is, the first thing is to find its gain, its voltage gain, right? We are looking for some characteristics, and that's the first thing we want to know. What kind of gain can we get from it, and then see what happens. So, how do we find the gain of the circuit? Well, we need to draw the small signal model of the circuit. Presumably the bias conditions are good. We have chosen V0 and V1 and everything else so that we have some current, we have some VGS, some VDS, the device in saturation, and now we can draw the small signal model of the device in saturation, and then we can analyze the circuit to see how much voltage gain we can get. Again, voltage gain relates to changes in the voltages, right? We have some change at the input, we have some change at the output. This change represents the gain. It's like this, right? This change divided by this change gives us the gain. So because we are interested in changes, we draw the small signal model. More precisely, because we are interested in small changes in the currents and the voltages and the signals and everything, we are allowed to draw the small signal model. Otherwise, we would have to use the big square law equation, and it's a little difficult to do that. Okay, so let's go ahead and think about that. Let's draw the small signal model of the circuit. Just remember what it looks like. I also refresh your memory that when we are drawing the small signal model, this is what we do. The microphone is represented by a simple voltage source. It's a time-varying voltage source, so it stays. The battery V0 is set to 0 because its value doesn't change with time. The change with time is 0, so it becomes a 0 voltage source, meaning a short circuit. Similarly, V1. And then we replace the MOS device with a small signal model. So let's go here and see. All right, we begin with the microphone. So here's the microphone. We call it V-in. It goes to ground because battery V0 is shorted out. Then we draw the small signal model of the device. So here's the small signal model of the device. The source is grounded also. Then we have GM V-in. GM V1 to be precise. I'm just substituting the small signal model for the device. GM V1. Let's see here. V1. And V1 is between gate and source. That's the small signal voltage. Then we have a resistor, or L, or D, that goes to AC ground because V1, the battery voltage source, is also set to 0. It doesn't change with time. And V out is measured from here to ground. So that's V out. Okay. All right, I'm going to play a little trick here. We see that RD has a particular connection. So let's change the color and see. RD goes from this node to ground, right? To all of this ground. So why don't we just cross it out here and draw it like this? It's the same thing, right? Instead of going around and coming down, I just drew it like that. Now what I observe is that the voltage across RD actually happens to be V out, right? V out is a positive here, negative here. RD is connected from here to here. So the voltage across RD is equal to V out. How much is the current through RD? Ohm's law. So this current is V out over RD. So far so good. In this direction, right? Because V out has a positive terminal on top of the resistor and a negative terminal on the bottom of the resistor. So the current has to flow this way. Okay, now let's go back to the input of the circuit. How are V in and V1 related? V in goes from this terminal to 0, to ground. V1 goes from this terminal to ground. So V1 and V in are equal. So V1 happens to be equal to V in. In finding the voltage gain, we are interested in V out over V in. So we have to eliminate V1. And this helps us eliminate it. GMV1 becomes GMV in. And now I can write a KCL at this node. So let's write a KCL at the output node. We have only two currents flowing from the output node. One is this guy, GMV1, which is the same as GMV in, and then another one flowing this way. And these two have to add up to 0. So plus V out over RD must be 0. There's nothing else, right? Because we took that out and placed it over here. So what does this tell me? It tells me that V out over V in is equal to, it goes to the other side, multiplied by RD, we have minus GM RD. So that is the voltage gain of the simple common source topology that we have seen. The gain is given by a negative sign, there's a negative sign here, GM of the transistor itself times the resistor that we have connected between the drain and the supply voltage, right? VDD, that V1. Okay, that's very interesting. Does this negative sign have any interpretation? Yes, it just means that the output is flipped with respect to the input. And in fact, we saw that a moment ago. We saw that when we drew the waveforms qualitatively, we ended up with V out going like this. V out is flipped with respect to V in. So that makes sense. That's how it ended up being. And then it's also given by the transconductance of the device, the strength of the device, because the MOSFET is trying to convert a voltage to a current. A voltage to a current. The stronger the MOS device is, the larger amount of current it produces for a voltage change, right? And we would expect that makes the gain higher. And then eventually RD itself, because RD does the reverse. RD performs current to voltage conversion. Right? We have voltage to current conversion, current to voltage conversion, and that's how we get V out. All right, that is the simple expression that we have for the voltage gain. We must remember this. It's always useful, and we will play with this extensively in the future. Our time is up. I will see you next time.